The goal of linear discriminant analysis, or LDA for short, is to find a linear combination of features to separate different classes. Ronald Fisher, born in 1890, was a British polymath known for his work in statistics and biology. He is also considered the founder of modern statistics. The terms Fisher's linear discriminant and LDA are often used interchangeably, although Fisher's original article described a slightly different discriminant that didn't make some of the assumptions of LDA. The LDA algorithm, which we will discuss today, is a generalization of Fisher's linear discriminant analysis. The fundamental problem that we are trying to solve using LDA is classification. In any classification task, what we really want to find is the class posterior, that is, the probability of the class K given the input X. From Bayes' theorem, we notice that the posterior is proportional to the likelihood times the prior. We are going to leverage this observation and assume that the distribution probability of input is equal to X given the class is equal to K is a multivariate Gaussian distribution. Keep in mind that the input X is a vector. We need to fit the Gaussian distribution for each class. The parameters of the Gaussian distributions that we need to determine are A. The mean of the distribution, B. The covariance matrix. To make things a little simple, LDA makes a second assumption, that is, the covariance matrix is the same for all the classes. In terms of the ability to classify, all we need is the likelihood and the prior distribution. Based on the assumptions that we made previously, we can obtain this information from the dataset. Let us consider a dataset with one output variable and two input features. The first step is to find the prior of a class from the dataset by dividing the number of observations that belong to a particular class K to the total number of observations in the dataset. Next, we estimate the parameters of the Gaussian distribution. In this example, the mean vector of each class is a two-dimensional vector. Next, we calculate the common covariance matrix from all the observations in our dataset. By calculating the mean and covariance, we have essentially fit two Gaussians to our dataset. We can use these Gaussians to make a prediction about new unseen observation. To make a prediction, we calculate the log of the posterior and pick the class with the highest value as our prediction.